Okay, so sorry for that technical glitch. Welcome to the Infinite Games Workshop. My name is Joel David Hamkins, and I'm the speaker today. I'm going to give a survey talk of Introduction to Infinite Games. So let me share my slides, and I'm sorry it's not going to be perfect because of this technical glitch, but we're going to make do. So here we go. I think if I maximize it, it won't be maximized for you guys. And so we're just going to work with it like this. I hope that's okay. So let me just jump right in then. This is the Infinite Games Workshop. And I have a whole bunch of different games I want to talk about. And please feel free to ask questions about any of them. Because I could go on for about an hour about each of these games here. And so if you have any questions, just feel free to ask, and we can take questions in the middle. But I just want to give you a taste of all these different games, which is kind of the way I think about the subject of infinite games. We're taking sort of ordinary games that people actually play in a finitary manner, but thinking about infinitary versions of them and working out the infinitary game theory of those games. That's what I like to do. So let's just jump right in. And I want to start with this etching that was given to me by one of my Oxford undergrad students, Django Pinter. And he called it recursive chess. And he made this etching for me, and you can see that there's chess pieces here on the board, but the chess pieces themselves are playing a game of chess. But they're not just playing a game of chess, because if you look at the board very carefully, you can see that those chess pieces are also playing a game of chess and so on. And furthermore, there's these larger pieces sort of in the background. And so you can see we're already several levels deep in this recursion. And Django made this etching for me. But he hadn't ever thought exactly about what the rules of recursive chess should be. And I think that's a kind of interesting puzzle, which is not yet fully resolved. So the problem, as I see it, is to invent the game of recursive chess. What are the rules of recursive chess? I mean, it seems like, okay, probably the queen is trying to capture the knight. But in order for that capture to be successful, they have to sit down and play a game of chess. And then the outcome of that game is going to determine whether that capture is successful. But if it's a failure, does that mean that the queen disappears? And what exactly is the position that they're playing from, and so on? And we want it to be probably a well-founded recursion so that the game is actually sensible to play and not, doesn't have sort of non-well-founded instances that would give an unresolved outcome. And so that's the kind of puzzle, is to figure out exactly what the position is that the recursive pieces are going to play and what are the rules exactly. And I made a blog post and put up about 6 different proposals depending on different ways of thinking about how it should work. Notice also that the colors have swapped, which might be an indication. But if you have a version of recursive chess in which the colors don't swap, then I'm open to hearing that. Although I think maybe any such rule you can always do it where the colors are swapped. So, okay, that's recursive chess. It's maybe not an infinite game, actually. It's a finite game, maybe, unless the recursions go infinitely deep. But that's exactly the kind of circular case that I was talking about. And so, right, I would love to hear your views on recursive chess. Okay, here's another game. It's a famous game. I call it Escape, and it's played on an infinite quarter board. And there's these 3 stones in the corner in the shaded region. And the way you make a move in this game, it's actually a kind of one-player game, I suppose. You pick any stone, and it splits into 2 and moves up and to the right. So that stone disappears from there and becomes 2, like that. And you can do it again with a different stone, or any stone on the board. You can split it into 2 and move up and to the right. And the goal of the game is to vacate the corner region. So you can keep playing. Can you completely vacate the shaded region is the puzzle. And well, let me give you proof. I actually coded up a version of this. You can play it online. And no matter how much you play, it's extremely difficult to make room. So right now we could play this one, but that would vacate the very corner, but not the other two. So we have to get these guys out of the way in order to, you can't ever double up the stones. So let me give a proof that in fact it's impossible to vacate the corner. And what I'm going to do is label all the squares of the board with these numbers. So it's like the geometric series on each row, starting with the right number there. And so the point of these numbers is that the moves preserve the total value. Because when you go up and to the right, the two stones there add up to the number at any cell. So every cell, the value of any cell is the sum of two values, the one above and to the right. And so making moves in the games preserves the total value. And the initial value is exactly 1 because it's 1/2 plus a quarter plus a quarter. But now what is the total value of the board? Well, this bottom row is adding up to 1 already. And the next one adds up to 1/2. And this row adds up to a quarter and so on. So the total value of the whole board is 2. But what that means is that since the shaded part has value 1, it means all the rest of the non-shaded part also has value 1. That's the other one that's going to make value 2. But that means you can't win, because if you were to have won, that would happen at a finite stage. And so you will have had only finitely many stones in this non-shaded part. And therefore, it won't add up to 1 because the total value of the non-shaded part is 1. And so if you've occupied only finitely many of those, the value of those stones is strictly less than 1. And so it's impossible to have value 1 on the unshaded part at a finite stage of play. And that means that you can't win. Okay, so, right. So it's impossible to escape. So there's another game that I call Buckets of Fish. And the way you play it is there's 2 players on a beach and they have finitely many buckets in a row. And there's an endless supply of fish off the boats. And on each turn, the buckets are in a row and you can remove 1 fish from one of the buckets. And then for the buckets to the left of that, you can add as many fish as you want. So you take 1 fish out of one of the buckets, and then you can add 2 fish to the next bucket to the left, and 3, and then 0, or 1 billion, or however many fish you want. You can add that many to the buckets to the left. And for example, take a fish from bucket 5, add 2, and 1,000 to bucket 2. It's finitely many buckets in a row. And whoever takes the very last fish wins. There are some fish in the buckets already at the start of the game. And what I like about this game is that, first of all, it's not obvious that it ends ever, of course, because sometimes people are adding huge numbers of fish to the buckets. And so wouldn't that make the game take much, much longer, because we're only ever removing 1 fish at a time, but possibly often adding many, many fish. And so it's a little bit of a puzzle. It's not very difficult, but it's possible to prove that, in fact, the game always ends in finitely many moves. You cannot have an infinite play of this game. And then also, it's kind of fun to think about what the winning strategy should be. So if someone asks me later, I can tell you what the winning strategy is, but maybe if you want to think about that game during the rest of my talk, then please feel free. How do you win? Would you rather be the first player or the second player, or does it depend on what you're looking at, and so forth? All right, let's turn now to the Chocolatiers game. This is a game that I created. And the way the game works is that the chocolatier serves up finitely many exquisite chocolate morsels on each round. The rounds will be unending and go like the natural numbers. And each round, the chocolatier serves an additional finitely many exquisite chocolates on the platter, and they accumulate as the game goes on. And on each turn, the glutton selects 1 from among those available and eats it. So finitely many come on, and you eat just 1, and then finitely many more, and you eat just 1. So, okay, and the question is, well, the glutton wins at the end after infinite play if and only if all the chocolates are eaten. Okay, so the glutton wants to eat all the chocolates. Okay, so chocolates are served, glutton eats one, more chocolates are served, glutton eats just one, more chocolates. How can he eat them all? I mean, it seems like we're sort of getting further and further behind. But of course, if you think about it in the right way, then even though the chocolates are steadily accumulating on the platter, the glutton seems to be falling further and further behind. But nevertheless, it's possible with strategic choices for the glutton to win. So let's describe how that goes. It's not very hard. Just imagine the serving platter as a queue, and you always eat from the front of the queue, and you put the new chocolates at the back of the queue. So this is the same as the standard restaurant stocking strategy. You know, you have the jars of mayonnaise and pickles and whatever in the restaurant, and you get the new stock in. You always put it at the back, and you always cook with the stuff at the front. And that way you make sure that you're never going to, I mean, it's the efficient way for making sure that the stock turns over. So, okay, so maybe this is the round one chocolates that are served. That's the first one we eat. The round two ones we put at the back, and we still eat from the round one guys, right? So we always eat from the front, and we put the new ones on the back. And now it's clear that the glutton is going to eat them all, because any given chocolate, we know exactly the round on which it's going to be eaten, because it's going to be finitely far from the front, and that's the round on which it will be eaten. Any given chocolate will be eaten at some finite stage, and so the glutton will eat every chocolate. Okay, well, what if the chocolatier serves up countably many chocolates on each round, right? So we have infinitely many on round one, and then infinitely many more on round two, infinitely many more on round three, and so on, countably infinitely many each time. Well, of course, the glutton can still win this one, although the queue strategy doesn't work anymore exactly like that, because if we put the round two chocolates sort of at the back of the queue after all these, we'll never get to them, because we'll spend all the rounds eating the round one chocolates, and we'll never get to the round two chocolates. But instead, we should, of course, just imagine this kind of winding chain, right? So the glutton is going to imagine in his mind that the chocolates are arranged in a kind of array, and then he's going to eat them in the order from this winding chain back and forth. And any given position in that array is at some finite distance from the start. And so we know exactly which round it will be eaten on, and in that way, he can make sure to eat all the chocolates by the end. Now, both of those strategies involve the glutton paying attention to the order in which the chocolates were served, and not just the set of chocolates on offer. And so if you think a little more deeply about it, it becomes quite interesting, actually. So is there a memory-free strategy? By that, I mean a strategy that at each stage depends only on what is available and not on how you got there. Right. Normally, when you talk about a strategy in a game, the strategy is allowed to know all the previous moves in the game, and that's sort of part of the information that's relevant for the strategy. But and we prove there is such a strategy for the glutton in this game. But the question here is, can we do it in a memory-free way? So can the glutton win if he doesn't know how the chocolates got there? Yeah. And there's various things you can say about this. If the chocolates are distinct, but there's only countably many possibilities. So in other words, if the chocolatier is infinitely creative, but only countably infinitely creative, so each possible chocolate is, say, labeled with a natural number, the menu item, and maybe not all the menu items are going to be served, but everything that is served is coming from the menu, then the glutton can win, because he's just always going to eat the lowest menu item that is available. And then there can't be anything left at the end, because once it was served, then for the lowest one that's left at the end, there would be a stage where it was the lowest one, and he would have eaten it at that stage. And therefore, there cannot be a memory-free strategy if there are only... I'm sorry, there is a memory-free strategy for the glutton if the chocolatier is only countably creative. Okay, but what if the chocolatier is uncountably creative? And in this case, you can prove that there can be no memory-free winning strategy for the glutton. And the way that you do that is, like, suppose, for example, the chocolates are coming from an uncountable set of possibilities. Then let's just suppose the chocolatier is always going to have put only 2 chocolates. Suppose the glutton has a memory-free winning strategy. And even in the case when the chocolatier puts up only 2 each time. And the glutton is going to pick one of them. So that's a kind of preference. In any pair, the strategy is preferring one of them. Yeah. So let's think about it as a preference, you know, the more delicious one or something, the more delicious looking one. Now, it can't be that there's a chocolate that has infinitely many things that are preferred to it, because then the chocolatier could put that chocolate and another one that's preferred to it on there, and the glutton would eat that one, and then he could replace it with another one that's preferred, and so on, and keep doing that forever. And therefore, the glutton would never pick that one chocolate that was infinitely preferred. I mean, that had infinitely many other chocolates preferred to it by the strategy. Okay, so therefore, every chocolate must have only finitely many other chocolates that are preferred to it by that strategy. And now you can just take any countable set of chocolates and close it under that operation of chocolates that are preferred to it. But that would still only be a countable set. And therefore, there must be some chocolate that isn't in that set, but that chocolate now has the property that all of those chocolates are preferred to it, because otherwise it would have been the other way and it would have been added to the set, but it wasn't added to the set. And therefore, we found a chocolate that has infinitely many chocolates preferred to it, which contradicts our earlier assumption. So therefore, there's no memory winning strategy in the uncountably creative case. Okay, but there's a further interesting development of this game. I really like this game because, of course, the first part is totally easy, but it becomes much more interesting the further you go with it. Namely, if you allow the glutton to know not only the current chocolates on offer, but also the very last chocolate that he ate, because he can still taste it on his tongue, right? He just ate it. So, of course, he knows that one. He just ate it. So he's got the chocolates on offer, the finitely many chocolates on offer, plus the one that he just ate. Then he has a memory-free winning strategy. I mean, memory-free in that sense, assuming the axiom of choice. So if you have the axiom of choice, then you can define this strategy. So if you want to know more about that, then ask a question about it later, and I can tell you the argument. Okay. Well, NIM is like one of the classic finite games. It's really a fantastic game. If you don't know about NIM, then you should definitely learn about it as soon as you can. The way you play NIM is there's finitely many piles of coins, and you take turns removing one or more coins from one pile at a time. And whoever takes the very last coin wins. You can take a whole pile if you want, or just one coin from the pile, or any number, but only from one pile. And the classic strategy is that you divide each pile height into sums of powers of 2, which is a way of saying that you're looking at it in binary. And then you make sure that everything is balanced. So for each such power of 2 subpile, you should make sure that there's an even number of such subpiles. So it's balanced. You want to leave a balanced position. And then the idea is that, well, if the other player makes a move, then you make a move to copy him in terms of that balancing. That's why you want them all to be even. So after this first move, it's a winning reply here, because I claim what's left is balanced because, well, we have 2 4s here. And then we have a 2 here and a 2 here. I mean, it's a 3, but that's really 2 plus 1, right? So there's a 2 subpile here and a 2 subpile here. So we have 2 4s and 2 2s, and then how many 1s? Well, there's a 1 and an extra 1 here and an extra 1 here and an extra 1 here, and then 2 more 1s here. So that's 6 1s altogether. So what's left is a NIM balanced position. Okay, well, of course, I want to play infinite NIM. If you have finitely many NIM stacks of ordinal height, then, oh no, my internet connection is unstable. I hope it works. Can everyone hear me?
Yes, no, yes, we missed a bit, but yes.
Okay.
No.
Okay, so the point is that the nim balancing strategy works even if the pile heights are infinite ordinals, because it has to do with decomposing the height as a sum of powers of 2. But every ordinal can also be written as a finite sum of powers of 2 using ordinal exponentiation. And if you just take the balancing strategy, so in exactly the same way, then can anyone tell me what the winning move is here? An ordinary nim game of 1, 3, 5, 7 is balanced because it has 2 4s and 2 2s and 4 1s. And those are all even numbers. So 1, 3, 5, and 7 is balanced. But also, therefore, omega and omega times 3, omega times 5, omega times 7 is also balanced. And if you think about these sums, then those are balanced too, because when you decompose omega plus 1 as a sum of powers of 2, it's going to be 2 to the omega plus 1. And so, anyone have an idea for the winning move? There's exactly one winning move. It's going to have to be on the omega squared, because that one isn't balanced by any of the earlier ones. And it has to be reducing it to 1 because there's an odd number of 1s here. And so we have to make it even by creating this one as a 1. But everything else is balanced. So that's the winning move here. And so actually the complete analysis of transfinite nim is very similar to the finite case. I found that quite interesting. Okay, let's go to the Sudoku game now. Of course, normally you think about Sudoku as a 1-player game, but I want to play it as a 2-player game. And we start from an empty board in the Sudoku game. And it's not about building a global solution. The Sudoku game is rather about never violating the Sudoku condition. So the Sudoku condition, right, is that on any row, the numbers shouldn't repeat. On any column, they shouldn't repeat. And on any subboard, they shouldn't repeat, right? Those are the Sudoku requirements. And so we're going to take turns putting numbers on the board in such a way that we never explicitly violate the Sudoku condition. And then whoever can't play wins. If you don't have a move, you lose. Okay, so the question is, who wins? Well, I guess I'm giving you the answer here. The second player wins if n is even. Of course, we were going to generalize this to much, much larger boards and eventually infinite boards, but let's just think about the n squared by n squared board when n is even. Then I claim the second player wins. And the proof is quite nice. It's a strategy stealing argument. I'm sorry, it's a sort of duplicating argument. Let's suppose red is first and red puts a number, then blue just copies, reflected through the center. So then maybe there's a red 2, a blue 2, a red 3, a blue 3. We just reflect through the center. And the point is that that's never going to create a new violation, because whatever violation blue had would have been a reflection of a violation for red. You cannot. So therefore, if red's move was legal, then the reflection of it will also be a legal move. And so therefore, this is a winning strategy for player 2. Okay. And if n is odd, then the first player wins. And it's a very similar argument. But in the odd case, there's a center. And now the reflection idea won't work, because if you play up something in the center and say blue plays a 3, you don't want to copy a 3 here because that would be illegal. But what you do instead of copying is you copy the tens complement. So the first player should, on the very first move, put a 5 in the center. And thereafter, the player should copy the other player's move reflected through the center, but with the tens complement. So 5 is first, and then if player 1 played this one, then the first player plays a 9. That's the tens complement. And if there was a 2, then we play 8, and a 3, and a 7, a 4, and a 6, and a 5 can be played in a 5. And again, the reasoning is that this tens complement reflection can never create a new violation of the Sudoku condition, because if it was illegal afterwards, then it would have been illegal before. Okay. Well, of course, I want to play infinite Sudoku. So we can imagine a Z by Z array with the integers, an integer lattice of integer lattice boards. Okay, so it's this sort of doubly infinite thing. And in this infinitary case, there's always going to be a move after finitely many moves. There's always going to be a move for one of the players. So that's not the right way to set up the game, maybe, but rather the solver spoiler variation. So the solver is aiming to create a global solution, and the spoiler is aiming to prevent that. And who wins, the solver or the spoiler? And the theorem is that the solver can win the Z by Z array of Z by Z boards in infinite Sudoku. And the way to prove that is to realize that, and so now actually one has to say, in finite Sudoku, you say, oh, there's no repeats on a row, column, or subboard, but no repeats is not quite the same thing as having a bijection in the infinite case, right? On a finite case, if you have no repeats, it also implies that you used every number. So the real winning condition here is that every row should have every integer exactly once, not just no repeats, but it should use them all. And similarly with the subboards and with the columns, right? So that's how you win. The solver is trying to create such a global solution. And the point is that, well, we can think about those conditions as requirements. Every row should have a 7 on it somewhere exactly once, and every column and every subboard. And similarly, not just with 7, but for every number. And the point is that if we've made finitely many moves so far, then for any such requirement, say we have a row and we want to put a 7 on it somewhere, but there's only finitely many moves have been made. So if there's already a 7 on that row, then I'm done. I met that requirement already. And if there isn't a 7 on that row, then I can just go out far enough to a part of that row that hasn't been used at all, and it won't have any conflicts with what's been played before, and I can just put a 7 there. So I can always add any given number to any given row at any finite stage of play if I want to, and similarly with the column and the subboards. And there's only countably many such requirements. I can also make sure to put some number in any given cell at any finite stage of play, because if it's empty, then, well, only finitely many numbers have been used, so there's going to be some number available that I can put into that cell. And therefore, the solver who's trying to create a global solution can simply meet all the requirements one after the other. He can make sure that every cell has a number and that every number appears on every row exactly once, and column and subboard and so on. And in that way, after the infinite play, he will have a global solution. It's interesting to think about larger cardinals like kappa cross kappa array of kappa cross kappa boards, and the same argument works in certain cardinal situations. But also, it's interesting to think about the kappa cross lambda array of lambda cross kappa boards. You can play Sudoku with these rectangles. So the smaller rectangles are arranged one way, and the boards are the full board is a rectangle in the other direction, and everything works great then. Okay, let's talk about Connect 4. This is a game I played as a child. You put the coins in the top and they fall all the way down with gravity. And you want to make 4 in a row, either horizontally, vertically, or on a diagonal. And okay, so whoever makes 4 in a row first wins. So let's play infinite, connect infinity. Say if the board is like omega by n, it has finite height. Yeah. So then the only way to make infinitely many in a row is to have, you know, the tail segment of a given row. But that's impossible. You can't win. No player can make a final segment of a given row because, well, first of all, you can't. I mean, well, one way to see this is let's have either player mentally divide the board into columns, pair them up, and then just copy whatever the other guy does on one column. You do the same thing on the other column that's paired with it. And that means that if it's yellow in one part of that column, it's going to be red in the other part. And that will prevent any row from being a win. So, and it doesn't matter who goes first. So both players can do that strategy. So they both have drawing strategies in this configuration. Well, what if it's omega by omega? So it's an infinite quarter board. And now you can win either vertically or horizontally or diagonally. You don't have to have the whole row, just infinitely much of it, starting from some point on. And now I claim still neither player has a winning strategy in this case. There's a couple of strategy stealing arguments. So first of all, the first player can't have a winning strategy because the second player can pretend to be the first player in the following way. If the first player makes a move somewhere, then the second player just says, okay, I'm going to ignore those finitely many columns up to that place. And then what's left to the right of that looks like a pristine board. And on that part of the board, the second player can pretend to be the first player. But if the first player ever happens to play on those columns again, then just play on top of him. And that will prevent a win from that sort of ignored part of the board. And meanwhile, on the rest of the board, the second player is playing as though the first player. And so if the first player did have a winning strategy, the second player would have refuted it that way. Okay, and then conversely, you can prove that the second player can't have a winning strategy because just let the first player pretend to be, no, let's see, how does it go? If the second player has a winning strategy, then the first player should just play in the first column and then pretend to be the second player on the rest of the board, except that if the other player ever happens to play in the first column, then just play on top. And so in that way, either player can sort of steal the strategy of the other one, and therefore neither of them can have a winning strategy. Well, there's a game of hex. You play colored stones on a hex grid like this, and the opposite sides. So blue is aiming to connect the two blue sides, and red is aiming to connect the two red sides. This is a game that Davide and I had played. And blue has won this game. Red goes first, but blue has won, which is an upset victory for this particular case because you can prove in hex that the first player has a winning strategy on any finite board, on any of these finite parallelogram boards. Okay, so it's a beautiful game, popularized by John Nash, right? No matter how you play, there's going to be exactly one winner, and therefore, by the fundamental theorem of finite games, exactly one player will have a winning strategy, and this strategy stealing means the second player can't win. So therefore, the first player must have a winning strategy. Okay. Well, there's an infinitary version of hex that Davide and I had looked at, and he wrote on it for his master's thesis at Oxford. So we play on the infinite hex board. And we're going to have talks later on about infinite hex later on in the seminar. Red is trying to connect the lower left to the upper right, and blue is trying to connect the upper left to the lower right, just like before. The question is, does one of the players have a winning strategy? We place the stones on there. We're trying to connect sort of ad infinity. And the theorem that Davide and I had proved is that infinite hex is a draw. Both of the players have drawing strategies if you start from the empty board. And this is, again, a kind of strategy stealing argument, shows that it can't be the second player who has a winning strategy, so it must be the first player if the theorem isn't true. But the second player has a drawing strategy because so what we're going to do here is we're going to have blue, who's playing second, reflect the red play. So red is playing first, and blue is basically reflecting that play through this green line, except it's not a perfect reflection because it's a hex grid, and so it's really a reflection with a half-step separation. And so this red is reflected to this blue, and this red is reflected to this blue, and so on. So we have this kind of reflection, almost reflection, but shifted a half cell. And what it means is that if red played in such a way so as to create a winning condition, so red is going, say, from upper right infinity and must eventually cross this green line. But then because of the reflective manner of the blue strategy that we just described, it will mean that blue has created this kind of wall from the lower right at infinity up to the green line. And because of the geometry of the way that red crosses the line, it must be that red crosses in this direction. But then it's easy to see that red is sort of trapped. And so it cannot be that there's this Z chain that's winning for red coming from the upper right of infinity, crossing the green line and going ultimately to the lower left, because whenever red crosses, in fact, red is trapped in this right half plane in terms of its connectivity to that upper part there. So therefore, there can't be any winning strategy for red in this game, and both players must have drawing strategies. Okay, so let's talk now about the fundamental theorem of finite games. So Zermelo proved in 1913 that every finite two-player game of perfect information, one of the players has a winning strategy. And I know several proofs of this, I think at least 4 proofs, and I'm going to go through a couple of them here. And so, yeah, so let's give those proofs. So what is a finite two-player game of perfect information? Well, I think David explained last time that when we say a finite game, we mean a game with a finite game tree. And he described, I think, this backpropagation proof. If we have a game tree of a finite game, so it's a finite tree, the terminal nodes are labeled with the winner of who won when play got to that juncture. And so we can just propagate that winning information up the tree. Working from the bottom, we're going to label a node with one of the players, with whichever player could win if play got to that node. So at the bottom nodes, of course, the winning conditions are already providing the label because the game is over at those points. But if you're at a node, then it's going to get your label if you can move to a child node that already has your label. You know, that's how we propagate the labels upwards. And the node gets the opponent's label if no matter what you do, you're still at a node with the opponent's label. So it's sort of hopeless for you to escape in that case. So we can propagate the information from the bottom up to the top of the tree, and the root node is going to get one label or the other because the tree is finite. And whoever it is can play so as to stay on nodes with their label. And the definition of how the labeling goes ensures that property. If you're at a node with your label and it's your opponent's turn, then there's nothing they can do about that. It's still going to have your label after they move. And if you're at a node where it's your turn and it has your label, then you do have a move to preserve that. So if you just keep doing that, then when the game ends, you're going to be at a winning node for you. Okay, that's the backpropagation proof. Here's the second proof. You should just avoid losing. So let W be the set of nodes from which the first player can win, from which the first player has a winning strategy from that position. If it includes the root node, then we're done because the first player has a winning strategy from the root node, which means they have a winning strategy in the game. So if it doesn't include the root node, then the second player is going to play so as to avoid those nodes that are winning for the opponent. So the second player should play so as to avoid nodes that are winning for the opponent, in the sense that the opponent has a winning strategy from those nodes. And the key point is that if you're at a position and your opponent doesn't have a winning strategy from that node, if all your moves lead to a node from which they do have a winning strategy, then they would have had a winning strategy from your node, because they could just assemble those winning strategies together to make a uniform strategy from that given node. Yeah, there's a subtle use of the axiom of choice in that argument, actually. And if you don't have the axiom of choice, then you can't prove that fact in full generality, although in certain circumstances you can if the space of moves in the game has a certain nature and so on. The reason the axiom of choice is allowed is because really for every child node, you need to pick a strategy in order to unify them together. And so there's this axiom of choice aspect to this particular argument. Okay, so the second player can win by avoiding the losing nodes. Now, here's a third proof of the fundamental theorem of finite games. Consider any finite game. And let's assume that all plays have the same length. We can do that because even if the game ended early on some plays, we can just put dummy moves in to extend the play a bit longer in a totally irrelevant manner, but it would have the feature that all plays of the game would have the same length. And now I can write down what it means for player 2 to have a winning strategy. Well, what it means is that for every move of player 1, there is a response, a good play by player 2, so that no matter what player 1 does, there's a response by player 2, so that, and so on. At the end of the game, that play is a win for player 2. That's what it means to say that player 2 has a winning strategy. So to say that player 2 doesn't have a winning strategy is just to put a negation in front of that statement. Okay, and now, but you know, in logic, we know how to put a negation in front of a bunch of quantifiers. If I can push this negation all the way through, and each of these quantifiers is going to swap to the other one, and I'm going to negate the inside part. That's just the De Morgan law. So when I push this negation, all these for alls become exists, and all the exists become for all, and then I've got now player 1 is winning instead of player 2. But now the point is that this statement, if you think about it, it says there is a move by player 1 so that no matter what player 2 does, there is a move for player 1 so that no matter what player 2 does, and so on, player 1 has won. But that's exactly what it means to say that player 1 is a winning strategy. And so what we've done is we've proved that if player 2 doesn't have a winning strategy, then player 1 does. And it's just the De Morgan law. So therefore, the fundamental theorem of finite games amounts to the De Morgan law of logic. One of the players has to have a win, because if player 2 doesn't, then player 1 does. Okay, good. So this argument also is very suggestive in the infinitary case. If you think about infinite games, I mean, games that have infinitely many moves, because it's very tempting to want to do the same thing in the infinite case. And maybe that would give you reason to think about what's called the axiom of determinacy, which is the assertion that all infinite games have a winning strategy for one of the players. And maybe you would want to look at that infinitary determinacy assertion as an instance of the infinitary De Morgan law, which you might think is sort of automatically true as a law of logic. But if you did that, you would be wrong, because in fact, we can show that there are infinitary games that you can define, even without the axiom of choice. You can define infinite games for which neither player has a winning strategy. And so one way of understanding that situation is that the infinitary De Morgan law is simply false, actually. It's false. But another way of talking about it is that actually, if you have infinitely many alternations of quantifiers, the only way of making sense of that statement is in terms of strategies. And so it's a little less shocking then in that case to say the infinitary De Morgan law is false. Okay, let's do some generalizations. Fundamental theorem of finite games with draws. Boy, I can tell I'm going to run out of time. So, okay. I thought it was important to talk about this sort of fundamental theorem stuff in this abstract way. I thought it would be helpful for what's coming later. It follows from the fundamental theorem that you get the fundamental theorem for games with draws. So in any finite game of perfect information, allowing draws, either one of the players has a winning strategy or both players have drawn strategies. This is what Zermelo, in fact, proved, and he was focused specifically on chess. But you can prove it from the other one. And the way you prove it is if you have a game with draws, suppose you have a finite game that allows draws, so some outcomes are draws, ties, then we can temporarily give those tie situations as a win for one of the players, say white. Now we've got a game without draws. And so it must be that either black has a winning strategy in this game or white does by the fundamental theorem. But for white to have a winning strategy in this modified game means that really white has a draw or better strategy in the original game. So we can see that in any game with draws, either black has a winning strategy or white has a draw or better strategy. But then we can also consider the modified game where we give the draws to the other player, to black. And so we see that either white has a winning strategy or else black has a draw or better strategy. And so the final conclusion is that, look, either one of the players has a winning strategy or else they both have draw or better strategies. That's the only case that's left. Okay, so this draw situation follows as a consequence. You don't need to redo the proof. You can just get it as a consequence of the other one. Okay. There's another generalization to what are called Clopen games. These are games in which every play ends in finitely many moves. You can have a tree with only finite paths. It doesn't mean it's a finite tree, though. Okay. But that's not possible if it's finitely branching. Every finitely branching tree with no infinite branch is finite. So in the Clopen game case, there must be positions that allow for infinitely many moves. And this issue came up when we were thinking about last session, when we were thinking about, say, chess positions with finitely many pieces. But the question is, if there's bishops or rooks or knights, then there's going to be this sort of infinitely branching situation where you're choosing from infinitely many possible moves. Okay. Another thing to say about Clopin games is that this is related to the context of Conway games. Conway has this theory of games that gives rise to the surreal numbers and so on, but all of Conway's games, sometimes Conway games are described as the most general kind of situation, but that's not true because in fact, all of his games are Clopin games. They all end in finitely many moves. So he's really only talking about Clopin games. They're called Clopin because the winning condition is open for both players. It's both open and closed. Okay, you can prove Clopin determinacy. The back propagation proof still works, except now it's because of the well-foundedness of the game tree. You're propagating transfinitely in the tree, not just finitely. Okay, but there's still a more general context, which is open games. So open games, a game is open for one of the players if all plays for which that player has won, the win is known at a finite stage of play. So this corresponds to the winning condition being an open set in the product topology of all plays. And then the Gale-Stewart theorem says in every open game, one of the players has a winning strategy. Might be the open player, might be the closed player. And the avoiding loss proof that I gave earlier actually proves open determinacy if you do it for the closed player. If you think about the perspective of the closed player wins just in case they never lost at any finite stage, right? Because the only way the closed player loses is if the open player wins. But when that happens, it happens at a finite stage. So the closed player can win an open game by never losing. And so this avoiding loss proof works. If the open player does not have a winning strategy from the root node, then the closed player can win by just staying on nodes for which the open player has no winning strategy. And that is going to continue forever. And so that's a winning strategy for the closed player. Okay, there's also this other proof, which is leading to the theory of transfinite ordinal game values. And so let's talk about that. Of course, as David has said last time, this is generalizing the idea of made in 2 or made in 3. The ordinal game value is measuring, in a sense, the distance to the win. So, okay. I'd said it like this, but I don't really like talking about that. The number of moves, it's not really the number of moves. That's not a correct way of saying it. Sometimes people are confused about that. They think game value omega means that somehow you're going to win in omega moves, but that's totally a wrong way of understanding it. Game value omega means that playing the game for the winning player is something like counting down from omega. It's the opponent is counting down from omega. But counting down from omega doesn't take omega many moves. It's going to end infinitely many moves because if you start with omega and you count down, then the first thing you say has to be some finite number, and then it's only going to last that many more steps, right? So it's not about the length of the game counting up to the ordinal, but you should think about the value as counting down. Okay. So, okay, these are open. Oh, wait, this is redundant. I'm sorry. Oh, no, I already defined open. Okay. Infinite chess is open because if you make a checkmate, then it happened at some finite stage. So it's an open game. Drafts is also open because the way you win drafts is you force your opponent into a position for which they can't move. And if that happened, it happened at a finite stage of play. If you play forever in drafts, that's a draw. Okay. In any open game, we can define the ordinal game value. And the game value of a position is just defined recursively. So if you've already won, the value is 0. If it's your turn and you can move to a position with the value alpha, then you take the smallest such alpha and the value of the original position is alpha plus 1. If it's the opponent's player's turn, and no matter what they do, they're going to get to a position with a value, then the value of the original position is the supremum of those values. So that defines the value of the positions recursively by induction on the ordinal. And some of the positions maybe don't ever get a value in that recursion, and that's fine. Those are the unvalued positions. And so the fundamental observation is that if a position has a value, then the open player can win by playing to reduced value. And the definition of the game values are defined specifically to ensure that the open player can always make it go down, and the closed player can't prevent it from going, can't ever make it go up or become undefined. So therefore, the open player is going to win infinitely many moves. If a position has no value, then the closed player can win by avoiding the valued positions. And this is something like the avoiding losing situation, right? So there's a connection between the various proofs of open determinacy. Avoiding losing is the same thing as staying on the unvalued positions. Those are the positions for which the open player has no winning strategy. Okay. So in any open game, one of the players has a winning strategy. Okay, so let's look at some examples now. I don't know if, oh my gosh. Okay, so it's already, I guess we started a little late, so we'll go a little over. Okay, so drafts, Davide gave a great talk last time. So this was a position that he showed that has value omega because it's black to move. There's only one black piece. It's this king. If he goes all the way up this blue ladder, then he's going to disappear and he's going to lose right away. But instead, he can jump, 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 and turn off and land on some square n. And what's left here is set up to have value exactly n. And so altogether, this position has value omega because black is in effect counting down from omega. He can announce any n that he wants by just jumping to that square n. And then the game is going to last n steps, and he's counting down by 1 each of those times. So he's counting down from omega, and he can start with whatever number he wants. Okay, so Davide and I had proved that every countable ordinal arises as the game value of a position. And the way that we proved that was embedding certain well-funded trees into positions of infinite drafts. And that's a completely general method that that we also used in infinite 3D chess. And it will also be used later on in the seminar when we hear the corresponding theorem for infinite chess, which I'm quite excited about. Okay. So, right. So let's go to chess. You know, I'm not going to have so much time to talk about all of this. And so would people rather hear about infinite chess or Wordle, infinite Wordle, or infinite mastermind? I think I can talk about some of these, but maybe not all of them. Is there any preference?
I prefer infinite chess.
Okay, so let's do infinite chess.
I mean, I would also like to see Wordle and Mastermind since they are rather new.
Okay, so why don't we do a little bit of infinite chess and then I'll try to get to the Wordle and Mastermind. Okay, so here's a position, a finite position in infinite chess with game value omega. These are all the pieces. Note that there's no white king, which some people object to. Chess players really don't like it. They say, where's the white king? But the point is that, you know, it's not possible for black to make checkmate here. So black is playing for a draw, right? In this position, the question is, can white make checkmate or is it a draw, right? If you don't have a king, then you can't be checkmated. So you're playing for a draw. I mean, your opponent's playing for a draw. Okay, it's black to move. There's many checkmates here. I think rook here is checkmate. Also queen here is checkmate. If it was white to move first, there's many checkmates available. And black's best move, it turns out, is to move his rook as high as he can. But it's going to be a finite amount, because every move is just going finitely. Yeah, but then white has this rolling strategy because there's a check move here and there's only one reply, and then check. This is a roller. Check, this forced reply. And white can just keep doing this, pushing the king up until eventually it's checkmate. And we can argue that that's the optimal line, that white doesn't have a quicker checkmate than that. And so therefore that has game value omega because white is going to win infinitely many moves, but the number of moves it takes is determined by black on his very first move. The n is going to be related to the height that his rook moves up. Okay, here's a position with value omega squared. We call it releasing the horde. So there's these pawn walls here and a supply of white kings. Both of the kings, white queens, I mean, the kings are over here, and there's this black rook. White wants to open the door and bring the queens in to make checkmate. Black doesn't have mating material over here. So it's sort of hopeless for black to checkmate the white king. And there's this black rook here that's kind of trapped and is about to be taken. But it's black to move. And so black is going to move his rook up as high as he can, 1 billion miles high. And then white is going to take it. And now the goal of white is to move these pawns up one after the other and then get this bishop out of there so that these pawns can move and the door opens and then the queens come in. So that's the idea for white, to open the portcullis, and get the pawns out of the way and open the portcullis. Okay. But the problem is that black has these harassing, these pointless, doomed harassment checks, because black can check the king. And white can't just run away, because then black will check him forever, and that will be a draw. So white has to play so as to stop the harassment. And the only way to do that is to move towards the rook. And eventually the white king will come next to the rook, but black wants to continue harassing later. So he better save his rook by moving it far away. And why not really far away? Because we have this infinite space out here. So black should move 1 billion miles away. Okay, and then white says, well, finally, I get to move a pawn in my strategy, right? But then black checks again. And again, white has to chase down the rook because otherwise it will be a draw. And so so that will happen for 1 billion moves, or however far the rook was away. The white king has to chase him down. And that's and eventually the white king is going to come next to the rook again. And then at that time, the black rook is going to go now 1 trillion miles away, or Graham's number away, some huge number, right? And then white says again, finally get to move a pawn in my tower here. Okay. And then black says, aha, check. And again, white has to chase down that rook. Otherwise, it's going to be a draw, right? So it's check, 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 check. Oops, I'm sorry. So check, 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 check until he catches up. And then black moves away. And now I had him move closer just because that's how it is on the board here, but he should probably move further to the right always, yeah. And then now is when white gets to move the pawn in the tower. Okay, and then harassing, check, 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 until finally he's caught up, and then move far away again, you know, a googolplex, many away, and a pawn. Oh, I see, we can bring the bishop out right away now, and then another round of harassment, and the pawn up, and then more harassment, check, 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 yes. And then the door opens. Okay, but there's this last round of harassment that happens here until finally now the queens come in, and it's check and checkmate. Okay, so that has value omega squared because the number of counting down from omega squared means that we went to some number ordinal times n, but n could be whatever you want, any finite number. But then when you go from omega times n to the previous one, you have omega times n minus 1 and so on, you're going to get n announcements that can be made later on from which you're counting down. The nature of counting down from omega squared means you have sort of one super announcement, which is the number of small announcements that you're going to be making, and each small announcement is the number of moves before the next small announcement. So the super announcement was the height of the original rook. That's the number of times he's going to be able to move this rook. And each small announcement is the distance that small rook went away. That's like counting down from omega times 3 to omega times 2 plus k. K is the distance the rook went out. So we can associate with the positions here ordinals, and the value is exactly omega squared because of that. Okay, so here's the sort of what I call the previous state. I used to call this the state of the art, but it's no longer the state of the art because of the amazing developments that show every countable ordinal arises. But this is the position that had value omega squared. And so let me not get into the details of this, but I'll just show you the pictures. Okay, this is the main black bishop that's going to go up, and it's going to be captured, and that's going to set in motion these rook towers. And these pawns are going to have to move up before the next tower is activated, and then those pawns are going to have to move up before the next tower, and so on. And ultimately, this white bishop here, which is red, is going to be released and make checkmate in the throne room. Okay, but meanwhile, between all that, we have the bishop cannons of every possible size. And the way the bishop cannons work is that there's one move coming out where the bishop comes out of the cannon, And that's when white gets to make progress by moving a pawn in the rook towers. But then what happens is that the bishop will enter one of these gateways. It came out of the cannon in such a way that it could enter these gateways. And the gateways are designed so that they have any desired length. And black is going to be able to make forcing moves one after the other for the entire length of this thing. So all of that is just a gigantic omega squared delay apparatus. The rook towers themselves are an omega squared value. And so altogether we're getting omega to the fourth because of this. Okay. So let's now go on to Wordle. So I'm hoping that many of you know how to play Wordle. You guess the 5-letter words, and then the letters either turn green if it's the right letter in the right place, or they turn orange if it's the right letter but in the wrong place. There's some code word you're trying to guess. And who can tell me the code word?
The error?
Error, yes, error. Very good. Okay, so I want to do infinite Wordle, or at least very long word Wordle. Right. Okay, so let's, before doing that, consider the nerdle variation. So words are now valid equations expressed in this vocabulary. So for example, here's nerdle played with words of length, I don't know what that is, 26 or whatever it is, 27. Or maybe I'd have to count. Okay, so we're getting some feedback here. You can see that there aren't any 7s at all in the correct equation, and there aren't any 8s or 9s, but there is a 1, and there's a bunch of 2s, I guess. And the equal sign is going to show up. Oh, we know where the equal sign is, right? And there aren't any pluses or minuses or timeses, but there is a divides. So I don't know if anybody can guess. Maybe it's too hard to guess. But I can just tell you this one. Okay, so that's the valid equation we were trying to guess. And okay, so I want to think about nerdle with extremely long equations, like 1 million letters. I mean, 1 million symbols or something, maybe even more than that. And the question is, suppose we play nerdle with equations of length 1 million, then how long will it take to win? Because if you think about it, there's an enormous number of valid equations of that length. Because, for example, I could put any number times 0 equals 0. Okay, so that's like almost 1 million digits in that number. So it's something like at least, basically almost 9 to the million. I mean, it's like, 3 less than a million, because it was times 0 equals 0. So I should subtract 4. So the number of valid equations is enormous, this enormous exponential, right? So that's the kind of space of that. And those are just trivial. I wasn't even using plus and times and so on. And so it's going to be many more. Okay, so the theorem that I was able to prove gives an upper bound on the length of play for optimal play. And the theorem is that the code breaker can win in 15 guesses at most. Okay, which seems like a very small number in comparison with what you might expect. But actually, if you think about it, you realize that in actual Wordle, like, you can often win in 3 or 4 moves, which is a sort of shockingly few number of moves. And the explanation for that is actually you get a huge amount of information from that feedback. And when the words are much longer, you get even more feedback from all the yellow and green information. And so you're getting a lot of information, and so you can still win fairly quickly. Okay, this is the proof. Start with any valid equation as the first guess. I'm sorry, I'm going over here, but we did start like because of that technical issue, so I'm feeling a little bit free to do that. And I think I'm realizing I never started the recording again, so oh well, that's that. Okay, you guess anything as your first guess. And now I'm going to ignore all the yellow stuff and just pay attention to the green stuff, but I'm going to keep all the greens, all the letters that were correct, I'm going to keep them, all the numbers or operations or whatever. And I'm going to use a totally new symbol on all the non-green cells, okay? And now someone might say, well, Joel, how do you know there is an equation like that? And the reason I know there's an equation like that is because the right answer is like that. Whatever I guessed, some of them turned green. Then there's another guess with exactly those green ones correct and using a strictly new symbol in all the other squares. Because that's what the right answer is like. So there must be at least one equation like that, and I'm going to guess any such equation. Okay. And I'm just going to keep doing that. For the third guess, maybe I got some more greens on the second guess. I'm going to keep all the greens. And on the other cells, I'm going to use a totally new symbol that hasn't appeared in that square yet. And how do I know there is a valid equation with that property? And the reason is the right answer is an equation with that property. So there's at least one guess that will allow me to continue. And therefore, I claim that is going to win in 15 steps because there's only 15 symbols. There's 10 digits and 4 operations and an equal sign. That's 15 symbols. And so in 15 steps, I'm going to know the value of every square because whenever I didn't get it right, I was using a new symbol in that square. So that can happen only 15 times. Okay, that's the Wordle theorem. And in general, it shows even in infinite Wordle, if the alphabet has size n, you can win in n steps. Okay. But what about an infinite alphabet? Of course, I want an infinite alphabet. Okay, now that proof doesn't work anymore. But if the dictionary is countable, you can always win infinitely many steps because you just guess the words in order from the dictionary and eventually it's going to be right. So therefore, if the dictionary is countable, you can win infinitely many steps. Okay. Well, what if you have a countable alphabet and the words are length omega? Then I claim, well, maybe you can't win infinitely many steps, but you can win by stage omega. Okay, you can win at worst at stage omega. At stage omega, you will know the answer and you can guess it then. Okay. And the way to do that is it's similar to the strategy that we gave for the Wordle theorem, except that because the alphabet is infinite, it might take you infinitely many steps to figure it out. But then at the end, you'll know what every cell should be, and you can guess at stage omega. You can show that some dictionaries take that long and cannot be won at a finite stage. And there's a kind of cardinal invariant here. What are the sizes of the dictionaries that cannot be won at a finite stage? And they're all uncountable. And their size at most continuum. And it's a kind of subtle, delicate question about how they relate to the other cardinal characteristics, such as the bounding number and so forth. Okay, let's go to mastermind and finish up. So mastermind is, I view mastermind as a kind of game from which Wordle arose. It's related to Wordle. It's more difficult. And it's similar to Wordle in that, okay, there's a hidden code word of colors, a color sequence, and you make guesses about it and you get feedback, but you don't know which one is right. So black means that one of the colors was the right color in the right place. So the orange one here was right. Okay. And the gray means that it was the right color in the wrong place. So for this guess, let's see, the yellow one was correct. So that's the black. And the orange color was right, but the wrong place. And the purple color was right, but the wrong place. So we have 2 grays, but the red one was totally wrong. So that's why we didn't get anything for that. Okay, and so forth. So the mastermind feedback consists of these 3 kinds of numbers. We know how many are correct. There's the correctness count. That's the total number that are correct. Just the number, not which ones, but the number of them. And then there's the rearrangement count, which is the number that could become correct if you were to rearrange the incorrect ones. And then there's the incorrectness count, which is the number that will be remaining incorrect even after any rearrangement of the incorrect ones. So it's sort of like the number of blacks, the number of grays, and the number of empties here. Okay, so the theorem that I proved is that if you have infinite mastermind with omega many colors and duplication is allowed, then the codebreaker can win at stage omega. And the proof is you play all possible monochromatic sequences together with the almost monochromatic sequences, so sequences that are all the same color except for one opposite different color. And if you play all such combinations, then you can determine exactly which cell is which color based on comparing the monochromatic one with the slightly altered monochromatic one. You can see how the feedback changes, and it gives you exactly the information you need to deduce what the color of that cell should be. So therefore, at stage omega, you can play it. But in the no duplication case, it's much more difficult. You can't do that monochromatic thing. And in the no duplication case, then for no countable ordinal does the code breaker have a winning strategy to win by that stage. And the proof of this is it's similar to forcing, if you know about forcing, because what you do, what the code breaker should do, I'm sorry, the opponent, we call him the mastermind, the person who's setting the code, should imagine that the true code is a kind of generic pattern in the sense of forcing. And then he's always going to answer that if the guess is, okay, this is the no duplication case, so the guess is just a kind of sequence of distinct colors. And we're always going to imagine in our mind that infinitely many of them are correct and infinitely many of them are incorrect. And then we're gradually going to make promises about the specifics of those. But given any finitely many guesses, we can always we only need to make finitely many specific promises, and therefore we can make sure to survive into any countable ordinal length by just keeping in mind that the actual pattern is this kind of generic pattern, and there's no way of guessing it by that stage. Okay. So in particular, there's not going to be any countable winning set of guess words. So a countable winning set of guess words would be a set of guess words such that if you know the feedback on those guess words, then you know the answer. There can't be any countable set. So this brings in the cardinal characteristic idea, because we can define the mastermind number to be the size of the smallest winning set for no duplication mastermind using words of length omega over a countably infinite color set. It's uncountable, and its size at most continuum. So under the continuum hypothesis, it's equal to the continuum. But the question is, well, what can we prove about it, say, in CFC? Is it always equal to omega 1, or is it the continuum, or is it in between? Can it be in between? And the answer to those questions is yes. There's some variance. This is the one where you allow duplication. This is the strategic mastermind number, where you look not just at the size of the winning guessing set, but rather the length of play, thinking of it in the strategic manner. This is the number when you only have the correctness and incorrectness count as feedback and not the rearrangement count. Okay, so it's always between Aleph 1 and 2 to the Aleph 0. So under the continuum hypothesis, these are just equal. But the exact value is not settled in ZFC. There's independence results. And this is a kind of summary of what I know about the possibilities. So the mastermind number itself is this one, and it's always the same thing as what's called the covering number, or the Martin number for co-enforcing. And that's consistently strictly in between Aleph 1 and the continuum. And these other mastermind numbers, these ones are all provably equal to the continuum. These mastermind numbers are all provably equal to each other and equal to the covering number. And these ones are provably equal to Aleph 0. So it gets into this rather difficult set theory, I think, even though we just started with a kind of infinite game situation. Okay, that's it. Thank you very much. Are there any questions? Oh, I am recording after all. I thought I didn't see that.
I guess maybe I would like to ask you maybe to elaborate on the chocolatiers game with the axiom of choice.
Sure.
How exactly you can use that. I was imagining some sort of like encoding, like for each set a representative who tells us like what chocolate to eat next.
Right, it's something like that. I think the proof that I know is rather using a well ordering of the chocolate types. So you well order the chocolate types. And the axiom of choice is equivalent to the assertion that every set can be well ordered. So let's well order the possible chocolate types. And now let me describe a strategy for the glutton. This proof only works in the case where the chocolatier is serving finitely many chocolates each time. Okay, not infinitely many, but only finitely many. So we have we're looking at finitely many chocolates. Okay, and what we're going to do, and we have the taste of the previous one in our mouth. Okay, we're going to look at what's there and we're going to put them in the order of the well order. And we remember how the one we just ate fits in that, and we're going to eat the largest one that's less than the one we just ate. Okay, so that's going strictly down in the well order. That strategy. I mean, if there is one, there might not be any chocolate available that's less in the well order than the one we just ate, in which case we eat the currently largest one. Okay, so it's a finite set, it's in the well order. The one we just ate cuts that set somewhere. We pick the biggest one that's less than the one we just ate. And let's think about how that works. The proof now, by the way, this argument is due I believe to Laver and Chichelski, I think. I have to look it up. I think those are the right names, though. So there was also a guy on Math Overflow who independently came up with this argument, but it turns out to be published already some time ago. But it wasn't called the Chocolatier's game at that time. It had a much more boring description of like how it worked and so on. So the Chocolatier part is my meager addition. Okay. Because we're going down in the well order, we're infinitely many steps. That's going to stop. So eventually we're going to move to the top, right? So now whichever one we ate and whatever is available there, those chocolates that are currently below are going to get eaten at some finite stage, because even though I'm adding possibly more, eventually everything below the one I just ate is going to get eaten because it will be the largest one that's less at some stage. I'm never going to skip them, right? At some point, they're going to become the largest one available, because infinitely many steps, there won't be anything left below what I've just eaten, because I'm going down in the well order, and that can happen only finitely many times. So therefore, at any stage, if I ate a chocolate, I am going to eat everything less than that chocolate at some finite later stage. Okay, but in particular, it means that any chocolate that's ever served, well, infinitely many steps, you're going to jump to the top, and therefore you're going to eat that one. So therefore, it's a winning strategy for the glutton. I don't know if that was clear or not.
Yeah, makes sense. Thank you. Yes, and thank you for the talk.
Sure. Thank you. You're welcome. Any other questions?
So I might have another question, and I was wondering, this is very interesting and fascinating stuff, actually. So I was wondering, how much determinacy do you need to prove theorems about the winning strategy in some of these games?
Right.
Because I was thinking, for example, if we consider the hex game, I can label each hex with a natural number or a real number, and then the game is essentially equivalent to the Banach Mazur game or something like that. And I think the same goes for most of the other games. For example, I can label each possible moves in the tree from a given position in infinite chess, still with a natural number or a real number, and so on. And so I just need full determinacy or projective determinacy in each of these cases.
Well, that's assuming that the winning conditions are Borel or projective or whatever. And in most cases, that's true. But it was an open question for a while, what the complexity of hex, of the winning condition in hex is. It was something that wasn't clear to me. So David and I were working on infinite hex. And the winning condition is asserting, right, the existence of this Z chain of a particular color. And for red, it should go this way, and for blue, it should go the other way. But that's an infinitary quantifier, right? So I guess it would be projective and fall under projective determinacy. But what we were interested in is it Borel? Because then we would have it in ZFC that for every position in infinite hex, we would know that one of the players had a winning strategy because of Borel determinacy, right? And I sort of suspected that it might be arithmetic or even much simpler, and it turns out that that's true now, and we're going to have talks later. Let's see, now, who is it who proved the hex thing? Was it Ilka, or was it Matthew, or Andreas? I can't remember which of you did the hex result now.
I think it was me.
Okay, thank you very much. So we're going to have a talk later proving that the winning condition in hex is in fact arithmetic. And therefore, in particular, it falls under the Borel determinacy results, or, it's much simpler than Borel. And so that was important in order to know. We already knew that the empty board was a win for the second player. I mean, sorry, is a draw. So we already knew the status of the empty board, but what we didn't know is what's going on, like if you start from some random position. And the point of that arithmetic winning condition is that it's going to help us to show that every position in infinite hex is falling under the determinacy results in CFC. So either one of the players has a winning strategy or both players have drawing strategies. I don't know if that answers your question.
That's perfect. Thank you very much.
There's another related topic, which is that sort of how complex are these games, and can we think of the games as playing a natural number? And for most of the games, that's true, but for drafts, it's not true in a way that Davide had alluded to in his talk a few weeks ago, because a play, sometimes in drafts, a single play is actually an infinite thing, because it's this infinite jumping, and maybe you had many choices about how to continue your branching pattern. And so the only way to describe what the one move was basically with this infinite sequence, basically a reel. And so the game tree of infinite drafts is sometimes up to continuum branching. So it's not really modeled with a game in which each move is a natural number. And so it brings us into this sort of realm of determinacy for games on the reals rather than for games on the natural numbers. So it's related to some of the things that you said.
By the way, since we are talking about determinacy, I wanted to ask you that you alluded in your talk about the existence of games which are undetermined, but they can be constructed without choice.
Yes.
Because I knew that it's notoriously choice and determinacy.
So with choice, the famous result is that you can refute AD using choice, because you can define a game for which the plays are always natural numbers. You can define a game using the axiom of choice where the plays are all consisting even just of zeros and ones, such that neither player has a winning strategy. So there's no ties in the game, but every outcome is either a win for one player or the other, but neither player has a winning strategy. So that's the sort of very well known. I mean, I can sketch the proof if you're interested, but what I'm thinking is something other than that, namely without the axiom of choice, I can produce a game. It won't be of that form where all the plays are either zeros or ones or even natural numbers, but in ZFC, you can prove that there is a game. So, I'm sorry, in ZF, without the axiom of choice, you can prove that there is a game such that neither player has a winning strategy. And it goes like this. So, so let's see, the first player should first of all play a set of real numbers, and the second player should play an element of it. And then the first player should play a non-determined game, if there is one. And then they should play that game. And the winner of that game is the winner of the game I'm defining. Okay. And now the point is that if the first player has a winning strategy, then they have to play a non-determined game and then win that game. But that's impossible. So therefore, the first player cannot have a winning strategy. So therefore, if the second player has a winning strategy, then in particular, they have to be able to choose a real number from any set of reals. And so the axiom of choice holds for sets of reals. And that implies that there must be a non-determined game. And so player one will be able to play a non-determined game. But then player two has to win that game. And that's impossible. So therefore, neither player can have a winning strategy in this game. And I never use the axiom of choice to define it. You don't need the axiom of choice to define it.
Wait, so how do you use the assumption of the existence of an undetermined game?
Not assuming it. If there isn't a non-determined game, then player one is going to have a hard time making that third move. But player two won't have a winning strategy either, because he won't be able to play the second move, which is picking a reel from an arbitrary set. Which implies, so if he could do that, then there would be a non-determined game, right? That's how it works. So it's kind of this, I mean, I'm sorry, it's not an interesting game to play, but it's a game that is designed specifically to be a definable game for which neither player has a winning strategy without using the axiom of choice. And so it's just, the point of the game is just to be that, and it is that. And so I'm kind of happy with it. Because it shows that De Morgan, it's an absolute proof that De Morgan way of understanding how determinacy works is not right. It's not correct to think that the De Morgan analysis of infinitary logic is giving us a reason to believe in AD. That's not correct, because if it were correct, it would imply that my game should have a winning strategy for one of the players, but my game doesn't have a winning strategy for other player. And I wasn't making any choice assumption or anything funny like that. So, right, that was the purpose of that game.
Thank you very much.
But maybe building on that, but we do, at least we don't know that ZF plus axiom of determinacy is inconsistent.
Right, sure. I mean,
Right.
I think it's probably consistent, because
Right.
even with DC, I mean, with the dependent choice principle, which is a little bit of choice, but it implies countable choice and so on. And you can even have that with AD. If infinitely many wooden cardinals is consistent, which is something that many set theorists believe is correct. So I think a lot of set theorists think that AD is consistent with CF plus DC even.
Right, then how exactly would you accommodate that with this constructing this game in ZF?
Well, that game exists in those ZF models, but AD isn't about, AD doesn't cover the situation of my game, because AD is just about
Alright.
games on the natural numbers. Sometimes
Okay.
we look at AD sub R, which is games played where the moves are real numbers, like as they are in drafts. The move is, I was arguing, is basically a real number. So ADR is the situation there. But my game, it wasn't even an ADR game, because we had to play a game, which is a set of real numbers, not a single real number. So it's another way of saying it is that AD for the power set of the reals is false, even without choice. Right. If you play games and the moves in the games are sets of reals, then there's going to be a non-determined game.
Okay, good to know. So then we have kind of an upper bound for how strong we can make AD.
Right. You can also prove, I think, AD sub omega 1 is also false. In other words, if the moves are countable ordinals, then this is also false. Without choice, you can provide a non-determined game. Any other questions?
I have a question. Maybe it's kind of what about mastermind, but you have to like guess like an entire binary tree or something. Like,
so you want the code words to be trees instead of in a line, or what? Or
yeah, so you know, like you have a binary tree and then you're gonna color the nodes all different colors or something, and you have to guess that whole.
I mean, the code word in mastermind
Oh, yeah.
is linear, but actually that doesn't really matter. It could have been a circle or some other shape. The shape doesn't affect the play in any way. So it could have been a tree already, and the play would be exactly the same. Unless you meant somehow where the tree would affect the play somehow. So I'm not quite sure what you would want.
Or like some kind of guessing uncountably many colors or
Oh,
something.
I see. Oh, yeah. I guess there's a version of Mastermind where you're only allowed to guess some. Like maybe you have to leave some blank something. Like I could imagine the code word is infinite, but you can only guess finitely many positions at a time and get the feedback. Yeah. So I don't know. I'd never thought about that, but that would be interesting. Or maybe it's like size kappa and you're guessing less than kappa, or on some ideal or something. That would be interesting. Actually, in the case of just omega and the code words, the guess words are all finite only. I mean, one would have to understand, well, what exactly is the feedback going to be? Because I guess it's just going to tell you, like, on your finite guess, how many of them are, fully correct, and how many of them are the right color but the wrong place, and how many of them are never going to be correct, even if you rearrange them. So you can still have the same feedback. Yeah, that would be interesting. Yeah, I encourage you to think about it. So we have the code word is an omega sequence of colors, and the guess words now are just some finite piece, right? Not necessarily from the front, but maybe, it's some finite piece way out there, or maybe just the finite initial segment. I guess maybe that would be, because it would be in the interest possibly of the code breaker to have a big guess as possible. I'm not sure if that's right or not, but it seems intuitively right that he should use as big a word as he can, although it has to be finite. So why not just extend it all the way to the left? Yeah, maybe you can figure out what the colors are. Yeah, so why don't you prove like you can always do it by omega or something like that? I'm not sure. I haven't ever thought about it, but it's interesting.
Yeah, okay. Thanks. Thank you.
Would that be similar to having like one extra color in the dictionary that is only used by the code breaker, but not by
the empty color or something? That's what you mean?
Yeah, the kind of empty color.
There's other versions where I think in actual Mastermind, sometimes they say there's an intermediate form about duplication, namely that the code word can't have duplication, but the guess words can. Right? It's a variation where it makes it slightly easier for the code breaker because he can guess things that will never be fully correct, but maybe they're more useful for getting information. And this is related to Wordle. There's really two dictionaries. There's the dictionary of allowed code words, and that doesn't include any swear words or politically sensitive words or something like that, because the New York Times removed those words from the possible right answers, but you can still guess them. You can like think up some really saucy word and it will be accepted as a guess in Wordle, even though it will never be the correct answer. And so it's a similar kind of situation where there's really two dictionaries: the dictionary of possible guesses and the dictionary of possible answers. And sometimes maybe you could prove that, like, is it true that, I have no idea, I've never thought about it, but for every dictionary of answers, is there a dictionary of guess words that makes it easier to win, or you can win more quickly or something? I have no idea if that's helpful, but it might be interesting to think about that.
Maybe we could think of like standard Wordle, and I'm sure that there could be like one best initial word, which is a non-English word, right? Like I think like usually New York Times is like slated
like
like
A-E-I-O-U or something.
Yeah.
Because then you would know exactly the vowels, right? But that's not a
Yeah.
word. But if you guessed A-E-I-O-U, that would be really useful. It's probably would be helpful, right? If you could guess it. So, right. Yeah, why?
I think audio is a very nice word for that.
Which word did you say, Andreas?
Audio. At least you know all the
Audio.
vowels except for E.
Yes, sure. I
Yes,
usually
but
start
I think that's.
Yeah, I think so. Yeah.
What?
I usually start with irate.
Yes, I think depending on what you want to optimize, there are also different best words. Like, is your goal to get the best average score, or is your goal to always finish with the highest certainty?
Right, it's true. There's different criteria, but also actually you can find people who make false statements about it because there's a kind of assumption that people make sometimes. Like even if you say if you want to win as quickly as possible, right? If that's the criteria, and I agree that that's, you know, maybe the more correct criteria would be maximize the probability of winning in 6, because that's what it means to win the game. Sometimes I'm annoyed in chess when they give a puzzle and it's like made in 2 or made in 3 or something, and you have to make this move like you're sacrificing your queen and so on in a way that's really obscure and difficult and dangerous seeming unless you really understand everything about it. And it does achieve the mate in 3, but maybe you're better off just winning in 4 because, like, aren't you worried that you make a mistake by sacrificing your queen? And so, you know, is the goal of chess to win, or is it to win as quickly as possible? I mean, I think it's just to win. And so from that point of view, the mate in 3 puzzles are not really about chess, it's something else, right? Except,
Well, but you need to look at the most forcing variation.
yeah, but
So
what if it takes longer?
if you do, but if it takes longer, it means that the opponent has more probability of finding counterplay and do something different, and
Yeah, I
then
mean, there's,
you are thrown off your variation, right?
yeah, that's the other danger, except like sacrificing your queen or whatever, you know, in some of these things you have to make these sacrifice moves would strike me, you know, I'm only a mediocre chess player, and so I'm reluctant to even pursue those moves very far. But some of the chess puzzles that I look at involve that kind of thing in order to get the optimal mate in 3 or whatever it is. And I'm always kind of put off by those puzzles because maybe that's a move that I wouldn't ever actually play in a game because it just looks too risky. Okay, but of course, if you analyze it fully, you know it's not risky because you know that, you know, the moves are forced or whatever, and so it's totally fine. But anyways, the point I wanted to make though about the Wordle is that if you have the criteria of winning as quickly as possible, then sometimes people say, oh yeah, there's this strategy that's the best possible, and they make claims about the best possible first word, for example, based on the idea of minimizing the number of possibilities that remain, right? But my view is that, okay, this is a kind of greedy strategy. If you can easily write a computer program that looks at the possible place that you can make and minimizes the size of the remaining dictionary that could be allowed, right? And so if you play at every step so as to minimize the number of possible words that it could be, then intuitively that's a pretty good thing to do, and it means you're going to win pretty quickly. But what I don't agree on is that that is provably the optimal play, because maybe it isn't. Maybe actually you locally make a move that doesn't quite minimize, but actually it's going to enable you, you know, 2 moves later to get much smaller possibilities depending on the answers that were given. And so, okay, I don't know for a fact that that happens. I would like to produce situations to prove that in certain situations it does happen. I think, yeah, I thought about that once, and I can't remember now if we actually came up with an example or not. So I want a word such that, you know, it has only a handful of a word with feedback such that it has only a handful of words that it could be, you know, using the standard dictionaries. And such that if you guess the one that minimizes, that it won't win in the best number of steps. That's what I want. So that you should guess rather a word that is slightly less optimal from the greedy strategy point of view, but actually is game theoretically more optimal. And I think that you can probably do that. And I'm not sure, but I'm guessing or hoping maybe that that's true. And what if that were right, it would show that a lot of the claims that you can easily find made about this greedy strategy are not actually right, maybe.
I guess that also, like, I think that there's some rules about, especially in Wordle, about whether you have to use the same, like whenever you find like your green letters, then you kind of need to keep them in the same position, or kind of keep
Oh,
any.
yeah, so that's,
right.
what is it called? Hard Wordle.
Right.
Is that what it's called?
possibly.
Hard Wordle is that you have to keep the green one. So the strategy that I gave, for the Wordle theorem was a hard Wordle strategy, right? Because we were always keeping the green. But my opinion about playing Wordle is that actually it's an inferior game. It's more interesting to play Wordle than hard Wordle, because when you don't follow that rule, then you're making these strategically interesting decisions about finding words that settle. The word isn't right because you're violating the hard Wordle property, but the word that you're guessing is giving you a lot of information about what the true word might be. Personally, when I play, I like to do it like that. I guess a first word, usually irate, and then I get the feedback, and then my second word is almost never a word that's going to be correct. But I want to get as much information about, what the correct word might be, aiming to win on round 3, right? So to sort of give up on round 2, aiming to win on round 3, because, that's a kind of challenging thing to do, to win systematically on round 3. I mean, I'm not winning systematically on round 3, but, I'm pretty close between 3 and 4. So, yeah.
I think possibly there's like an example. I remember once there was like the solution was like Brian, and so like the fourth, the second last letter as options, and maybe that could be an example. Like someone, if you get it at the second,
I see.
You need to find.
I see. You're talking about proving the phenomenon I was just talking about, but for hard Wordle. Yeah, I think that should be better. Yeah.
Right. And so there would be a very clear difference that, well, if you can just try one word, there maybe getting 5 out of 6 letters like right is actually a problem. Yeah.
Right. Because is it right? You can have these words that agree on the last 4 letters, and that you don't know what the first letter is yet. And so if you play hard Wordle, then it's going to take you the number of guesses. But if you play the other way, you can guess one word that uses all those. So I see. Okay, great.
Thank you.
I just wanted to add, I don't remember exactly where I've seen it, but I've seen also people already discussing this before and talking about shallow solutions versus deep solutions to Wordle, which I think is referring to kind of this.
I see. Is that the same? What, the shallow is the greedy algorithm, or what?
Yes,
yes. Right. I see.
As far as I remember.
I just posted a link that seems to just claim that even the deep question is completely settled. They've gone over all possible game trees essentially.
I see.
Someone's bothered to spend that computing power, and so
the greedy solution is optimal then, game theory?
No. The greedy solution is not optimal. That's definitely true.
So that's what I was.
But at least for some definition of the greedy solution. Yeah.
I mean, you minimize the size of the dictionary that remains. So that's what I was meaning by the greedy solution.
Yes, that is not optimal. Yeah.
Okay, I see. That's great. Okay, perfect. So I guess one can, what is the infinitary analog of that? I mean, one can look at, it's not just size, I guess, because, these are infinite things, but they have maybe Lebesgue measure or something, or, is there any advantage to minimizing the Lebesgue measure of the words that remain? No idea. Maybe it's just not even sensible. Yeah, I guess maybe one could hope to prove that doing that won't even win, I bet. Yeah, so let's make a dictionary so that if you minimize the Lebesgue measure of the remaining possibilities, that is not even a winning strategy, say at omega. Right. So I bet you that's true. Yeah, that would be an interesting theorem. So I mean, the infinitary analog of this greedy strategy or shallow strategy, however you want to call it, maybe should be about the measure of the dictionary, right? Assuming it's Lebesgue measurable. I mean, if I'm thinking of the infinite case, right? So we have natural measure on the dictionary, and on the subsets of it, and are they measurable? I don't know. But, anyways.
So a possibility could be that if you have to guess in n moves, you have a vocabulary of n+1, and all the all the solution starts with any of the n+1 on the n+1 vocabulary.
I'm thinking of the situation where we're playing Wordle with an infinite alphabet for words of length omega. So it's playing on bare space, basically.
Yeah, so I was thinking that after the first letter, all the letters are all the same, but the first one, there is one word for each one of the possible letters, so you have to go through all of them every time.
I'm not quite following you. Are you trying to describe a winning strategy, or are you?
No, something that you cannot win in the end in a finite number of moves.
Right. Yeah.
Especially if you play the hard version of it. Right. Something like if you have just one, well, for example, an easy example, if you have just one move to guess, and you have rain, and could be brain or train, and you cannot guess which one it's.
Right. So it was, yeah, so one of the theorems that I mentioned was involving this generic code word in order to provide a situation where the strategy wouldn't win at any finite stage. So we provide a dictionary. I mean, we provide a code word and dictionary and so on, so that you can't win at a finite stage. But you can always win at omega. So yeah, I'm not quite sure what to think about this measure thing and whether that's a good analog of the greedy algorithm or not. So. All right, any other questions? Right, so maybe, you know.
I guess maybe just the last thing that came to me now with talking about variations was with Nerdle. I was thinking maybe how much harder it would be, or the bound of 15 would be higher if at every point during your guess you wanted the guess to be a valid equation.
No,
Then I'm
but you do.
thinking
That's how Nerdle, that's required in Nerdle. All the guesses have to be valid.
yes, but from what I saw, did they have to be like the true equations?
Yeah, the words are the true equations. That's a requirement.
Okay, but I think the guesses, as far as I understood the argument, do not have to be valid words then.
No, the guesses also have to be true. You know, and the proof, my proof that I gave. So that this is the question, you know, well, Joel, how do you know there is an equation, a true equation like that, right? That's what I had said. And the reason why I know there is a true equation that keeps all the greens and uses a new symbol in all the other places is because the right answer is like that. So there's at least one true equation that obeys the hard Nerdle requirement, and that's going to be the next guess.
Oh, right. Okay.
So all the guesses are true in that case also. The thing about Nerdle, it's a little different than Wordle in that it doesn't seem to have a natural infinitary version, because, I mean, unless you allow many, many equal signs, I suppose, where they're all equal to each other, I suppose, then you could make an infinite equation, I suppose, you know, with many equal signs in between. But like if I put, you know, I couldn't write something equals and then infinitely many. I mean, maybe, I mean, I could do something
Maybe
like,
if you use p-adic numbers.
yeah, maybe like 1/2 plus 1/4 plus 1, you know, equals. I could do geometric sums or something. Yeah, maybe, yeah, because one wants to do infinite Nerdle, but with true equations. So it's all about these infinite sums and differences and stuff, but they have to converge and be equal. That would be interesting. But I guess you would want it like Z then, because then you could have them on each side.
Oh, yeah, probably.
I don't know. Yeah, I'm not quite sure how to think about infinite Nerdle as opposed to infinite Wordle. But I think ultimately, though, that Nerdle is just a special case of Wordle, and that Wordle is the more general one. So whatever rules you decide about infinite Nerdle, it's just going to be an instance of infinite Wordle in this abstract way that I'm thinking about it, where you have a dictionary and a set of allowed words and so on. It's just that the words are going to have mathematical symbols in them instead of letters, but so what?
Or what if you just like omega equals 0, 1, 2, like the whole set or something?
Right, yeah, something like that. Oh, I see, with braces and so on, like set equations. That would be fun. But even that, like, it still falls under the most general conception of Wordle, which is, you've got sequences of symbols and a dictionary. And I think it's still covering all such cases, basically. So.
Also, it's kind of nice to add like infinitely, like add more equal signs, because after all, like if you have like Z tiles, kind of, you can figure out where the equal signs are in like just 2 guesses. Like there's like 0 equals 0 equals 0 on the, if equals on the odd places, and then on the even
Right.
places.
Oh, I see. Yeah,
Not
that's
too
right.
bad. It's quite doable in that sense, at least to figure out where the equals are.
Right. Yeah. Great. All right, maybe we should wrap it up, and then let me just announce the next talk. Let me look at the calendar here. The next talk will be on November 2nd, and Ilika Torma will talk about the complexity of the winning condition in infinite hex, as we mentioned, showing that in fact it is arithmetic, which answers a question that Davide and I had asked in our hex paper, and I'm going to be really glad to learn about this result. So that's November 2nd, which is in 4 weeks. Is that right? 4 weeks from today, I think. It's not 3 weeks, right? 1, 2, no, let's see. What have we got? Oh my gosh. 1, 2, 3, 4 weeks from today. So next month, I hope you all come back, and we'll hear about infinite hex and the complexity of the winning condition in infinite hex. So.
Thank you very much. See you next month.